Hello and welcome to lecture number 6 of Photo and Non-Photorealistic Rendering. I am your instructor as always, Leslie Eisted, and in today's lecture we are going to talk about a different kind of rendering, and that is the technique known as rasterization and the use of shaders. But before we get to that, just a few things to note. First is make sure that you've seen that assignment 3 has been posted to Brightspace. This is going to be making use of some of the things you're going to learn about today. So using not ray tracing to actually do some cool rendering. And then use these techniques to actually create some interesting scenes. I've specifically asked you to use one of several renderers for that assignment. So in particular, I've asked you to use either Unreal Engine, Unity, or you can use Houdini and the Mantra renderer, but if you're using the Mantra renderer, make sure that you turn on micropolygon rendering instead of ray tracing. But that being said, if there is a different tool you would like to use, please let me know, and we can take a look at it and see if it's the right kind of tool. The next thing to talk about is tutorials. So we've been running tutorials so far as just a period of time where I am available. If you have a question, stop by the Zoom meeting, stop by Discord, and you'll get an answer right away. And if you need to have a video chat during that period of time, then we can do that. I think after having some discussion with some of you that it would be valuable if we actually had some demo videos to help with some of these tasks. So starting this week, I will be posting some tutorial slides that are going to be a curated list of how-to videos off of YouTube, which I think will be really, really helpful for you to doing some of the tasks for the assignments or just getting your hands around some of these bigger ideas. Now, sometimes these might be videos I record, and sometimes, Slide Effects puts out a great video about how to use their tool. We're going to use their video. So there will probably be several hours of content posted through those slides as well, and they will be posted on Brightspace. Two other things. So this is the last lecture you will have before reading week, and I hope you have a really great reading week. And when you return from reading week, there will be a midterm, and the midterm will take place during the tutorial session, and it will be through Brightspace. A few things that I can say about it is it's going to be a quiz in Brightspace, and you will be able to know your score right away. So there's no long answer questions where somebody has to go off and grade them. It's all multiple choice, true, false, fill in the blank kind of stuff. And I will post more details about that, maybe some review slides to Brightspace over the next week. So I think that's all the announcements we have for this moment in time. So let's dive in then to our actual content for today. All right. So we've spent the last 5 lectures really talking about ray tracing in greater depth. So looking at the algorithms, looking at the math and the lighting equations, and breaking down the different lighting effects that we see in real life and how they are replicated in a ray tracer, and looking at some of the different algorithms for global illumination. And what we note about ray tracing is because it's actually tracing the light through the scene, you actually get a very photorealistic result. Now, I do want to take that and put a pause on it and say, it sounds like I'm saying ray tracing guarantees a photorealistic result. That's not true. It doesn't guarantee you a photorealistic result. If you use poor materials, if you don't compose your scene, it's not going to look photoreal. There's more photorealism than just using a ray tracer. We'll talk more about that later. But ray tracing does have the potential to produce really photorealistic scenes, which is nice, because we are actually simulating a lot of the behaviors of light interacting with different materials. And that gives us those more realistic appearances, or at least it can. Things like this. So this is the same mesh, and we've modeled it 4 different times using 4 different materials. So we've got gold on the one end, and then we've got silver on the other, and then in the middle we have glass and we have diamond. And we're using global illumination here, so you can see there's caustic effects that are visible on the ground in the shadowed areas. And in general, because we're also using an environment map, this looks pretty real. I mean, it looks like it was done in a photo box with carefully structured lighting, but it looks very convincing. But it's a little problem. And that is ray tracing is actually really, really expensive. And this is a theme that we've been talking about since the first day, is that ray tracing is really expensive. It is really expensive. And there's many different optimization techniques that we've talked about. We've talked about bounding boxes. We haven't necessarily talked about bounding box hierarchy, but it's a similar idea. We've talked about KD trees. These are just methods to subdivide the world so that when you have a ray, you're querying a portion of the world instead of the whole world. So you're trying to reduce the number of ray object intersection tests that you actually have to perform. But even with those optimizations, ray tracing is still really, really slow. And I'll show you how slow in just a minute. So you might be asking, but I've heard about real-time ray tracing. Don't they have Zelda Breath of the Wild as like a ray traced game? It's like, yes, actually there is a thing called real-time ray tracing. It is an entire area of research, and it's a pretty cool area of research actually. And we're going to talk a little bit more about this when we return from reading week actually. There are some optimizations that you can do that can improve the performance of a ray tracer to the point where it's actually usable in a game. But they usually come at a cost, and that's the cost of quality. We are doing better these days, but it's still not always the same quality as a traditional ray tracer. Now, the other thing that lets us do real-time ray tracing is the fact that your graphics card has an amazing computation unit on board that's capable of usually performing thousands of computations in parallel, and that really, really helps with real-time ray tracing. And if you go back, 15 years ago, 20 years ago, this really wasn't possible because the hardware simply didn't support it. So we've got hardware support, we've got little tricks and concessions that we can make in the ray tracing to make it actually work in real time. And there are lots of game engines that actually do support this. Now, I think Unreal Engine 5 does, and I'm not too certain about 4. So it is possible, but there's a cost. So to give you an idea of ray tracing is slow, so let's go back to this image here. This is not a complicated image. I think we can all agree. There is a back plane, there is a ground plane, and there are 4 cups that don't actually have that many triangles that I remember. Now I've done some smoothing on the meshes because they were quite faceted, and I didn't like that appearance because it didn't look photoreal. But it's a very simple scene. Okay. This picture took 4 hours and 7 minutes to render using bounding volumes. And when I rendered it with a KD tree, which is just options that you can choose from within Houdini, this took 4 hours and 13 minutes. Now you may be like, oh, so that means KD trees are slower. Yeah, not quite. So these two numbers here, even though they appear to be different, I would actually say that these two algorithms took roughly the same amount of time. The reason why I would say that is because it wasn't a perfect test. I only ran it once, and there may have been other things in the subsystem, in my operating system, that were running that I wasn't aware of while I was actually doing the rendering. And in particular, one thing that I do know that was different between these two renders here was that the bounding volume hierarchy test was done when my monitor was off. So nothing was actually being displayed onto the screen. And the KD tree one was rendered with the screen on and I think Chrome was open. So there were other programs running and there were other computations going on which could have potentially reduced the performance. So I'm going to consider these two approximately equal. Now this was done with the Mantra renderer inside of Houdini, which is its default render. About the same. It's still 4 hours though. That's a lot of time. 4 hours for one image that didn't actually contain much interesting content. So how long does it take to render something more interesting? I think my record for this class so far was 29 hours for one image. And if memory serves me, when it got to like 85%, I looked at it and I was like, you know what, it looks good enough. And any additional rays that are being sent aren't going to give any meaningful contributions to the image. A little bit of noise is okay. So I just terminated it because I didn't want to wait another 6 hours. So ray tracing is really, really slow. Is that the only option that we have for rendering? Well, obviously not, because up until very recently, games were not using ray tracing. They use a completely different technique. You might have heard of it before in a previous course, the rendering pipeline or rasterization. You may also hear this referred to as shaders. And what this is it's just a different technique for taking the mathematical description that is a mesh, which it is a mathematical description. It's a set of vertices and a set of edges, faces that we are rendering. We want to display them onto the screen, and they are describing, you know, some kind of 3D model, and we want to project that onto a flat screen, and there's going to be some math involved here. So rasterization is the art of projecting those triangles onto the screen and then applying some kind of texture or material to them. And shaders are a big part of this rendering and rasterization pipeline. And what they are, and you've probably heard of this before, is they're just little programs. I'll show you some. And they run at different stages of the rendering pipeline. The two shaders you've probably heard of before are your vertex shaders and your fragment shaders. And sometimes fragment shaders are called pixel shaders, but they're effectively the same thing. But what these are, they're just little programs that we run at different stages when we're trying to take this mathematical description of the mesh and project it onto the actual screen. There are many other different kinds of shaders, and we will see some of them, but not all of them. Now, I did actually turn on, so if you go into Houdini, and I'll show you here in a minute. So this was our original scene, and I wanted to render this with bounding volume hierarchy, and I wanted to render this with KD tree using ray tracing. And then I wanted to enable the micro polygon rasterization, which is not ray tracing. It is a different rendering algorithm that we're going to talk about. And I wanted to see how long does it take. So if you go into Houdini, and this is something we'll look at a little bit later, under render view, this tab up here, so it's hard for me to see the screen. And then you click right beside it says Mantra IPR. There's a little menu button. If you click there, and then you go under rendering, you can see here it says rendering engine, and I've chosen micro polygon as opposed to ray tracing. And that is going to use a different rendering algorithm than ray tracing. And that's all you have to do. Then you hit render, of course. And when I did that for this scene, it took, yes, I know this one is very noisy. I was using this for something else here. When I did that, with micro polygon rasterization, this took 3 hours and 48 minutes to render. Again, very similar to the other results, but it is a little bit less, which is what I would expect. Now, why isn't it significantly amount less? Because video games don't take 4 hours to render one frame. Nobody would play that video game. Obviously, we're able to do things like Unreal Tournament running at 60 frames per second, and it looks beautiful. So the reason why this one was so slow is because of how the shaders are implemented for Houdini. They are doing rasterization, but then the fragment shaders and the vertex shaders are actually performing ray tracing operations. which means that you get beautiful, almost identical results, but you don't really get the performance improvement. It's interesting. So if we were to use something like Unreal Engine to do this or Unity to do this, it would run a lot faster. It's just the micropolygon rendering in Houdini is just not that fast because they're actually trying to reproduce ray tracing within the rasterization, which is mostly possible. Oh, excuse me. So what I want to look at today then is this rendering pipeline. We're going to look at it from a very high level, and then we're going to dive into some of the specific details in a little bit greater detail. So if we look at this from the top view, there's 4 big components to our rendering pipeline. We have the application, which is what's actually generally producing the initial geometry. This is something like Unreal Engine or your game engine or Houdini. That's what's actually you're creating your scene in. Then we have the geometry, which is performing any manipulations to the actual scene, so moving it, animating it, and so on. And then we have rasterization, which is going to be projecting it onto a 2D screen and applying any colors to it. And then the screen part, which is the actual sending the frame buffer from memory out to the physical device. So let's take a little bit of a closer look at some of these different things. So first we're going to take a deeper look at the application part of the rendering pipeline. And again, this could really be anything. So we already mentioned that it could be a game engine, things like Unity, things like Unreal Engine, things like CryEngine. These are all examples of applications that are used as the front of the rendering pipeline. It's typically where you're going to model your scene. It may even be where the final scene gets displayed, so the actual game itself. And the application actually performs some of the tasks. So it could be used for the actual creation of the models or the scene. It can be used to create the animation or compute the animation. So for example, in a video game, you would have the key controls and the mouse controls would be interacting with the game to play a specific animated sequence. And so that's going to be handled in the application phases. What motion do I need to apply? What bones do I need to move in order to actually get to the next state that we need to render? Applications also handle things like collision detection. That's actually a really fun one because how we do collision detection is actually very similar to some of the tasks that we do in ray tracing, just as a fun aside. An easy way of doing collision detection is to encase all of the objects in a tight sphere, and then instead of trying to determine, does this complicated object, this is a battery case apparently, intersect with this other complicated object, a spoon. You could try to do this, but this would be a really expensive computation right up, like does this spoon intersect this? Instead, what they do is they wrap a sphere or a cylinder or some kind of bounding volume around each of the objects, and the idea is the bounding volume would be much simpler to compute collisions with, and then they say, hey, does your bounding volume intersect this bounding volume? Yeah, that's done by the application. So those are all things, and other things that we tend to do in the application level would be any of the spatial subdivision optimization. So our arc trees, our KD trees, our bounding volume hierarchies, voxels, R trees, B trees, anything that's going to improve the performance of things by doing some kind of subdivision. That will tend to happen in the application part. The next phase of the rendering pipeline is the geometry phase, and this is actually a pretty big one on its own. There are several steps as part of the geometry phase. So what's going to happen is the geometry part of the pipeline is going to be passed a bunch of meshes, models, materials, and information from the application. And then the geometry, it's also going to be passed cameras as well, and lights, all those things. The geometry phase, the first thing it's going to do is it's going to actually do some transformations from one space into another. So you might remember there's things like there's model space coordinates, there's world space coordinates, there's viewing coordinates, there's screen coordinates, image coordinate systems, and we've got to somehow navigate from the model space coordinates all the way up to the screen space coordinates, where we're finally going to see what we're rendering. And the geometry pipeline is actually going to perform a lot of these transformations. So the first thing it does, of course, is takes the models and the cameras, and it's going to actually transform them so that they're in the same coordinate system. So this would typically be moving all of the mesh models, all of the lights and everything from their own coordinate spaces, either into the camera's space or into world space. And if you put them into world space, then you're going to want to put the camera into world space as well. So that is the first part of the rendering pipeline for the geometry phase. And we've talked about these things before. The next thing that we're going to do is we're going to do some lighting computations. Now you might be like, but we haven't tried rendering anything yet. You're right, we haven't. But sometimes we can perform certain aspects of the lighting computations earlier in the pipeline, and it will save us time later. So right now in the geometry pipeline, it's pretty common to do per vertex computations, and we might actually do a lot of per vertex lighting. So for example, I might want to know, if I have a light source here, I might want to know, well, what is the per vertex lighting contribution? Now, why would I only do it per vertex? Because later on, when I'm in the fragment shader, instead of having to do it for every single pixel like we did in ray tracing, we can just interpolate from the vertices. That's a pretty cool shortcut. So we can do some lighting computations here. We can store that in a texture or apply it to a texture. We can apply ambient lighting. Lots of different vertex level lighting can be done at this point in time. And then what we want to do is we want to take the viewing volume that was created by the camera, which creates that frostum. And I don't think I took a picture of the viewing frostum, but you know what, let's draw one here just to remind you of a viewing frostum. It's going to take a minute for Journal to open. Apparently it crashed last time. I don't want to do that. So let's create a viewing frostum. So we have our camera, and it sends rays out into the world. And we have a near clipping plane. Right there, there's my near clipping plane. And then we have a far clipping plane. And what this creates, and I'll kind of shade it in yellow, is called a viewing frostum. And the shape of this is a truncated pyramid. So it's a pyramid where we've cut the top and cut the bottom off. There you go. That's our viewing frostum. The problem is the coordinates inside the viewing frostum are kind of wonky because of the fact that it's projected out from a singular point. And so in the projection part of the geometry pipeline, what we're going to do is we're going to project and transform that frostum, which is what we call that funny shape, the truncated pyramid, into a nice cube. Because it's easier to process. It's going to be easier to project that onto our screen space coordinates. So that's what we're going to do. There are this sounds very complicated. So if you're doing any kind of code in OpenGL, there's the GL projection matrix, which you can make use of. It's not something you have to like memorize off the top of your head. And if you did want to see what these projection matrices look like to project the frustum into this unit cube, if you go back, I think it was to lecture 2 or 3, we actually have several of the projection matrices in there, and you can find them, of course, on the web as well, if you wanted to do it by hand. So now we have everything in this nice unit cube. We've taken care of the camera's field of view. We're going to actually do the clipping. So here's the problem we have. And I'm just going to grab some random objects off my desk. Some of them are clear and some of them are not. So I have this clear lid, and I'm going to pretend that this clear lid is my screen. And I'm going to pretend, oh, that's a really bad choice of object because it's green. Pick a thing, anything. Scrunchie. It's not green. I have a lot of green things. So we have this model of a scrunchie, and it lies such that it's half visible in the screen, or would be half visible in the camera, and half of it is not visible in the camera. The problem is that for all of these triangles that are not sitting in front of the screen, we're not going to see them. So why would we do any computations with those triangles whatsoever? They're pointless. So what the clipping phase is going to do is it's actually going to take that projected cube that we just created with the near clipping plane and the far clipping plane, and it's and then the left and right boundaries, the top and bottom boundaries, and we're going to cut. I mean, literally clip anything and discard everything that lives outside of it. So this half of my scrunchie that is sitting halfway outside of this frustum here is going to get cut off and thrown away. And that way, all of the triangles that are left are ones that we could actually potentially see. Whereas the ones that live outside that region, we could never ever see them, so we might as well get rid of them. And that's going to help improve performance a fair bit because it's less computations we're going to have to do later. Now, what happens if you have a triangle or a quadrilateral that actually sits on both sides of the line? So you have half of the triangle on one side of the clipping plane and the other half on the other. What do? You could just let it be. Another thing that people tend to do is they will actually trim the triangle. So they'll actually cut a piece off of it. And there are algorithms that you would have to apply in order to do that because, of course, there are different ways that you can actually trim a triangle such that you end up with, you know, things that you don't want. So, for example, if this is our clip, oh, I don't like yellow because you can't actually see it. Let's do a red clipping plane. And if this is our triangle, and this is what we're keeping in the shaded area, then when I clip the triangle, I end up with a quad. So we have to take that into consideration. You could, by the way, if you discover that when you clip the triangles that you'll turn the triangle into a quad, you can actually then tessellate it and you can get, you know, parts A and parts B if you wanted to. You don't necessarily have to do that. So that's what clipping is going to do. It's going to remove everything that doesn't live inside the world volume. And then the final part of the geometry pipeline is going to take that viewing frustum and it's going to project it into screen space. So it's going to, it's called the window viewport transformation. So we're going to take things from where they are and we're going to transfer them to the window for the screen space. Now what's interesting about this is that when you're dealing with computer graphics traditionally, we think of coordinates. I'm just going to erase some stuff here. I don't know why this program won't give me a second page. When we think of coordinate systems with graphics, we think of the Cartesian coordinate plane like this. There's z-axis here, so I've got z, this is x, and this is y. And then this point right here, 0, 0, 0. And then this is x negative and y positive, y negative, and so on. So the important thing here is that 0 point tends to be in the very center of our volume. But if you actually look at windowing systems and viewports, the 0, 0, and this is true for image-based manipulation as well, 0, 0, even if it's 3D volume, tends to either be the lower left corner or the upper right corner. And the reason why I don't want to tell you it's always the lower left corner is because it's really dependent on the system you're using. Some systems will have it as the upper right corner and others will have it as the lower right corner. And it's important you know what that is. So generally what we're doing though is we're going to take this here and we're going to shift it over and up or over and down. So it's not too terrible. The other thing that might happen is a scale operation might happen because they might not be in the same scale. Or maybe you want to show more of the world. There's lots of different things you could do. Okay. The next part of our lovely rendering pipeline is the rasterization phase. And this is where we actually start to draw things. This is where I have all of these triangles and they've all been converted such that the vertices of the triangles now live in the screen space coordinates. They do have a z component. They do actually have a depth. We kept that because we're going to need it. So we have those triangles whose coordinates are converted to screen space. And now, and they're all going to be, they're all in that correct area, but now I actually want to draw them onto the screen. So what we're doing in the rasterization process is we're actually going to take that beautifully mathematically described triangle and we're going to draw it as pixels on the screen. Rasterize the image. Now, how this typically works, there's many algorithms, but a common one is called scan conversion. And if you're not familiar with the word scan, it's called scan line because that's how old TVs used to work. So old projection, you know, CRT cathode ray tube TVs, they'd project the first line of color and then the next line of color and the next line and the next line and the next line. So they call them scan lines. Scan lines. Each row is called a scan line. So in scan conversion, what you do is you start at the top of the triangle and moving left to right along the scan line, which means all your y values are equal. We're going to draw each pixel that is lying inside of the triangle. And then once we have drawn all of the pixels for that scan line of the triangle, we move down to the next scan line, and so on and so forth. And so you end up with this triangle being turned into this pixelated one here. So how this would actually look, because it doesn't really make a lot of sense. If you think about it, this is smooth. How do I choose what this does? So we know where the position of each of the pixels are, and we could kind of just draw a grid over top. Now, in this particular diagram, I'm using the intersection of the horizontal and vertical lines to be the positions of the pixels. So I start with this scan line here. This pixel, not in the triangle. This pixel, not in the triangle. This pixel, in the triangle. So I render it. This pixel, not in the triangle. Not in the triangle. Done scan line. And then I go down to the next scan line. Not in the triangle, in the triangle. So I draw it over here. In the triangle, I draw it over here. In the triangle, draw it here, not in the triangle. No. And then that process repeats. And that's a high level picture of what the scan conversion algorithm is doing. But now we have, our beautiful smooth triangle has now been rendered as pixels on the screen. Now, ideally, this is very exaggerated here, obviously, because we need you to be able to see this. But when you actually look at this on the screen, you shouldn't really be able to tell that this is any different from the nice mathematical description, especially if you're sitting, at a proper distance away from your monitor. The two should look very similar. You shouldn't be able to see the pixelation. Now, to be fair, that in itself is an interesting story because you might see the pixelation depending on your monitor. If you have a lower resolution monitor or poor quality monitor, or if you're sitting like right in the monitor's face, then you would be able to see the pixelization. But I'm going to tell you right now, I'm sitting in about, 45 centimeters away from a 38-inch ultra-wide monitor that's like 4K. It's greater than a 4K resolution. I don't see the pixels. I'm not going to see them. So that's how we take a triangle's description and we render it on the screen. And that's actually really, really fast. Because we're not asking now ray pixel intersections. We're just saying, is this in the triangle or is this not in the triangle? We don't even care when we're doing the rasterization process, or at least that algorithm, what the z-value is. It's just send a straight ray. Is this in or not? If it is, pixel. If it is, pixel. That's it. Really easy. The problem, though, is that we do still need to think about Z, but for a different reason. And the reason why we need to think about Z is objects can be in front of each other. And so when an object includes another object, you can't see the pixels of the object that are behind. So how do we actually keep track of the Z values to make sure that we see only the things we're supposed to see? So for example, I have a red triangle and a blue triangle here. Technically, they're similar triangles. And the blue triangle is in front of the red one. When I rasterize this, I need to make sure that the blue triangle is visible and the region of the red triangle that is behind the blue triangle is not visible. So what we do is we keep track of the z-value, the current z-value for each pixel in something called the z-buffer or the depth buffer. And the idea is that as you rasterize each triangle, you put, you look at that pixel and you say, okay, is the z-value of this particular triangle at this particular pixel, is it in front of my current value in the z-buffer at that point or behind it? If it's behind it, don't bother. If it's in front of it, then you're going to actually render it down. So let's see what that means. So let's suppose that we actually started by rendering the blue triangle. So we do here, okay, it's badly drawn here because it's just slides. But let's say this one was actually in the triangle. So there's my pixel for it. And then I go down to the next scan line for the blue triangle and I get bop, 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 those three little pixels there. Okay, blue triangle rendered. And now in my z-buffer, let's suppose, that the blue triangle has depth or a z-value of 10. And let's suppose that positive z is coming out of the screen. And then I go and I try to render the red triangle. So I get this pixel here, and then this pixel and this pixel. And then when I come to draw this pixel right here, I note, okay, yes, this is a part of this red triangle. And when I go to the depth buffer to check whether I am allowed to draw this pixel or not, I see there's something already in the depth buffer. And its z-value is 10, but my red triangle's z-value is 0. So since I am technically behind what's already in the z-buffer, I just don't rasterize it. We ignore it. And then we move on to the next scan line. And again, so this one is in front, so we put it in. This one is in front, so we put it in. And then these three here, there's already something in the Z buffer that's closer to the camera or the viewer than the triangle I'm trying to rasterize, so I can stop. Now we have triangles on the screen, and we had to do significantly less effort to get them there. Now you might be like, oh, so this is really easy. No. There's some interesting issues that can actually come up, and this is going to reflect upon a topic we talked about much earlier in the term, and that is the fact that you are doing all of these mathematical computations on a device that has a fixed amount of precision to store values. That means that a computer cannot just store an arbitrary number of digits of precision. There's a limit to it. So as you're doing multiplies, divides, adds, subtracts, and so on and so forth, of floating point numbers, some of the precision of those numbers is going to get lost due to rounding. And when we were doing ray tracing and, comparing if two things were equal, we didn't say, are you exactly equal or are you exactly zero because of this? We always did, are you within epsilon, so some small value of the other one. And if you are, we assume you're equal due to rounding errors. And this plays a role to create something known as z-fighting. What happens is you've got a bunch of surfaces that are either nearly coplanar, so you might think of them like pages of a book, or they are coincident in some way, like maybe they cross like this, or maybe they're sitting like this. And what ends up happening is due to losses of precision, when we are doing the depth tests and doing the rasterization step and trying to use the Z buffer to figure out which triangle's in front, the rounding errors make it so that these nearly coplanar or nearly coincident surfaces, sometimes one wins, but sometimes the other one wins. And so you end up with a really noisy interspersed triangle from the two different surfaces. So let me show you what z-fighting looks like. And I'm sure you've seen this in games. It's pretty common, actually. So we have two planes. We have a red plane and a cyan plane. And the red plane should be just a little bit on top, so it should be visible, not the cyan plane. But what you're actually seeing here is the fact that precision errors in the computer are making it so that the depth tester for the rasterization phase of these two planes is sometimes having the cyan plane show up in the front and sometimes the red one. So this is z-fighting, or fighting in the depth buffer. And it happens, and I have seen this in many games. It's not uncommon at all. How do you solve this particular problem? Oh, and if you're sitting there thinking, but ray tracing doesn't have this problem. Yes, it does. Actually, it really does. And again, it comes down to precision. And so how do we solve this issue? So there are lots of potential ways that you can actually reduce this. One of them is don't create things that are nearly coplanar or coincident. Just don't do it. If you are applying a label, and this is the example that I always think of when I think about fighting in the Z buffer, is if you're applying a label to like a bottle of wine or something, and you want that to sit right on the surface of the mesh, consider shifting it a little bit away from the mesh. Actually, if you look at a lot of games and early rendered images from like the 90s and the early 2000s, and even today to a lesser extent, you'll actually see that like the labels on a lot of bottles are actually sitting quite a ways off of the object. And if you're wondering, why do they do that? Well, it's to prevent fighting in the Z buffer. So one of the things that you can do is just add a little bit of extra padding between the surface and the label that you've applied to prevent the fighting in the Z buffer. Other things that you can do is reduce the depth of the scene. So instead of the scene having like this depth range like this, bring it in a little bit tighter so that the values are all really close together and the amount of lost precision is significantly less. Another thing you can do is bake all the textures together so you don't have to worry about this. Yeah, that's Z-fighting. It's really fun. I should find a game that actually has it. I'm pretty sure I know I've seen it in Ocarina of Time, and I'm pretty sure I've even seen it in Breath of the Wild. Like I said, it's actually pretty common. And if you're sitting there thinking, well, it should be really noticeable because it doesn't matter what angle you look at, you'll see the same pattern. Actually, what's interesting about Z-fighting is as you move around a surface where their Z-fighting is actually happening, the pattern that is shown, like which surface, will actually change. It's really noisy and awful. So during this rasterization phase, this is the kind of the final phase before we display it onto the screen. The last thing that we're going to do is we're going to run the fragment shaders. And what they're going to do is they're going to take any information that was computed from the vertex shaders earlier in the pipeline, the geometry part, and they're going to take information like textures and they're going to combine it together to compute what is the final color for each of the pixels in the actual image. Now, when we actually display it onto the screen, kind of an interesting thing is that we have these things called frame buffers, and there's a front and a back. And the idea is you render your image into the back one, which is not currently being displayed. That lets you render into the back buffer, finish rendering into the back buffer, and then you swap the buffers. I think it's GL swap is the OpenGL command. I haven't done it in a while. But what that's going to do is it swaps the buffers, and now your image that you had fully drawn into the back buffer gets pushed onto the front and then actually gets displayed onto the screen. And then you can draw into the back buffer again. So that's pretty cool. I think it's pretty cool. So the pipeline that I showed you before was actually a really restricted, a really simple pipeline. It was missing a lot of details. So this one is one I borrowed from Wikipedia's entry on rasterization and the rendering pipeline. And I want to show it to you and kind of explain some of the different things that you're seeing here. So what you've got down here, these parts are all a part of the geometry. So you've got your vertex shaders, your animations, any transformations. So going from the model space coordinates to the global coordinates or the viewport coordinates, they're all happening down here. And then you've got some tessellation and some other shaders that are running. And these are things that are going to take something where you've got, like, let's suppose you're using 15 triangles to render a mesh, or 15 quadrilaterals. This tessellation phase is going to give you the ability to actually tessellate it further, which means break it up into smaller and smaller pieces, and more often than not, actually break it up into smaller and smaller triangles, which is what we want. Then we have the geometry shader, and we'll talk in greater detail about that in a little bit, but that's going to let us do some manipulations of our geometry after we've actually done some computations on it. And then we do this perspective transformation, so we're taking it from the world space coordinates and using the perspective view transformation matrix. Then we do our clipping, and then we have the actual rasterization process. After we've done the rasterization, the pixel shading process is also the fragment shaders, where we finally compute the final color. And then there's alpha blending and things like that that happen just before we dump that into the back buffer. Lots and lots and lots of things are going on here, and I feel like even this is still there's things missing. What's really interesting about this pipeline diagram that I'm showing you is that a large number of these different steps are programmable. And what that means is that you can exhibit some control over what happens in those steps. So for example, vertex shaders, hull shaders, geometry shaders, these are all areas where you can write little programs to control what's happening. The only places where you cannot do that is the red ones. In the red areas, you cannot program them yet. But maybe in the future we can change that. So what I'd like to do now is actually take a look at some of the different things that we can do with ray tracing, and how do we do those similar things with this rasterization and shaders. And we've already seen how we actually got the triangles to render onto the screen using the scanline conversion methods and z-buffering to determine which is actually visible. But the next question is, how do you actually do things like shadows and lighting and reflections and refractions and all of these different things that we can do fairly trivially with ray tracing? So shadows for ray tracing, just so we remember, is that after you have found the point of intersection between the ray and the object, you're going to send a ray from that point to each of the lights in the scene to determine, is that light visible from this point? And then based on that, you can compute the contribution of that light to the color of that point on the surface of the object to figure out the final color of the pixel. Now, what's interesting is that within this very customizable pipeline, as we see here, you can technically still do that, actually. These pixel shaders and these vertex shaders here, it's absolutely still possible to actually do ray tracing within them. You can send rays. You can do the ray computations here to actually do the lighting contributions. And in fact, some rasterization techniques, some shaders do exactly that. But you don't, of course, get the performance boost that you would get because you're still doing ray tracing operations. So we actually have several other ways of doing things like shadows. And how we can do them is doing things like shadow volumes. You might have heard of something called stencil buffers, shadow maps. These are all techniques within this rendering pipeline that we can use to compute shadows without actually performing the ray object intersection tests that we were doing with ray tracing. So I want to talk a little bit about the stencil buffer technique, just so you have an idea as to how it works. So like there is this Z buffer, and what a buffer is it's just a place where you can store stuff. Like this. This is a battery box. It is a buffer for batteries. So there's also something called the stencil buffer, which on some systems, they're all just implemented as a depth buffer that you can specify the color depth of. And the idea is we can actually use the stencil buffer to help us render shadows. So what you're going to have to do is for every light in the scene, because remember each light can cast shadows, we want to render the scene from the perspective of the light. Now why we would do that is because if the light cannot see that object, then that object is in a shadow of the light. So we render the scene from the perspective of the light, and we use it to create a depth map. And the depth map is going to tell us which of the objects that exist in our world are the occluding objects, which things are casting shadows in this scene. So for example, I guess that one actually has batteries in it. Let's choose one that doesn't. Shouldn't take batteries. So I've got these two little objects here, these two little boxes, and if this one is closer to the light, then it is partially occluding this one underneath. So when I render the scene from the light's perspective and create the depth map, I will have this being the depth rather than this, because this occludes this. When you've got that, you can create an actual shadow volume. So you've got the top of the shadow volume being the occluding object's depth, and the bottom of the shallow volume can be an infinite distance away. It doesn't have to be an infinite, some large number distance away. And then you can actually create a shape all around the foreground object, according to the light, to create this actual volume. And then how we're going to make use of that is we're going to load the stencil buffer using a depth fail or depth pass technique. And what they do is they're going to check for every triangle we can see in the image, does that triangle lie in the shadow volume or not? And if it lies in the shadow volume, then that would indicate that this is in shadow, and if it's not, then it's visible to the light. Normally what we do is that if the stencil buffer is not 0, then some point P on your triangle is in shadow. But if the stencil buffer value is 0, then that means that you can actually see this particular pixel, and we should do the lighting contributions as normal. You can kind of think of the stencil buffer as a mask. We are masking out where the shadows are and are not. So, and wherever they are not, we do regular lighting, and wherever they are, then we do shadow lighting. So this is actually from the OpenGL tutorial site. It's a great diagram. I've actually modified it a little bit. So this gray area, very roughly, is the shadow volume that's being cast by this green object here. Now, obviously, this line here should actually come up to this corner here. But this shadow volume that we have, anything that lies in the shadow volume is in the shadow. So A is not in the shadow volume, therefore A is not going to be, well, A is going to have the contribution of the light from over here. C is not in the shadow volume, so C is going to be lit by this light over here, but B, shadow, not lit. And what we're going to do is we're computing how many times we cross the shadow volume's boundaries between us and the object. And then the count of those things is going to tell us whether that thing is in the shadow or not. So it's pretty neat. And there's, as I said, there's depth pass, there's depth fail, there's many different techniques that we can actually do to produce the stencil buffer. And I don't have an example here because it just draws a shadow. The one thing I do want to say about doing this technique, it's not perfect. I mean, and this is one of the things. Ray tracing really does give you that edge when it comes to producing realistic shadows and realistic lighting contributions. Things like doing the stencil buffer for shadows, things like doing shadow volumes and shadow maps, they're not perfect. There are times where the shadows will be really noisy and they should be perfectly smooth edged. There will be times where there are certain parts of the object that should have a shadow and they don't. This is really an imperfect idea, but it's usually good enough. Especially, I will say this, especially if you're doing something like micro polygon rendering where you have really, really, really tiny triangles, like sub-pixel size triangles, then it's actually, it works reasonably well. And it's fast. That's the thing that we like. This is fast. So then we talked about reflections and refractions. And interestingly, again, you could just do the ray tracing operations within the shaders. Absolutely. And again, Some rendering pipelines actually do this, because why not? Especially if you're not doing anything in real time, it doesn't matter. The other alternative is to actually use the stencil buffer again. And the idea is, what you're going to do is you want to render the reflected scene. So if I have this box is actually kind of shiny. I know I'm not sure you can quite see that. But if I want to figure out what the reflection is going to be on this surface, then what I'm going to do is I'm actually going to put the camera somewhere here, such that I then render the scene as if viewed from this object. So I render it, and I can store that in a texture somewhere. And then what I'm going to do is I can use the stencil buffer to mask the regions from the viewer's perspective where that reflection scene would be visible and where it would not be visible. And then I'll use the stencil buffer to determine which computation is being used for this triangle to compute the final color. And for anything that lies in the reflected area, I would then be grabbing the information I stored in the texture for the reflection and combining that with the material of the object to create the final appearance of that thing. Which in this case is just this funny little battery box, which I'm going to try not to drop. And refractions kind of work the same way too, because you're seeing through something. So you need to see through it, and you need to actually know what you're going to do. Now, how we typically handle transparency, because we want some of the front object and some of the scene that we see behind that object, is we handle it actually later on by doing, in the pipeline, by doing something known as alpha blending. And we've talked, I guess that was in this course. That was the VFX course, I think, that taught you a bit about alpha blending. But the idea behind alpha blending is we're going to take some percentage of the color contributions from the object that we're seeing through, and we're going to add that to a percentage of the contributions from the things that we see behind us. So we do this alpha blending to get that transparency effect. And we can do this using the stencil buffer, which is kind of neat. But, big but. So the shadows kind of worked out. There are some issues with noisy, blocky, pixelated shadows, and there's various ways to solve that. But reflections and refractions done with the stencil buffer, they're not so good. There's a reason why we like ray tracing more than these techniques, is because ray tracing actually will give you the proper reflection that you want and the proper refraction that you want. Whereas if you're using the stencil buffer, I don't think it provides nearly the same quality of reflection that you would get. So those are our major things that we have. So we know how to render it on the screen. We know how to give shadows. We've seen you can do reflections and refractions. What about things like textures and bit mapping? Because, you know, things have pictures on them. Things have bumps. This actually has bumps. I'm trying to shine it into the light here so you can see it, but these buttons are actually little bumps. So how do you do texture and bump mapping? Actually, this is a big part of the rendering pipeline, is actually utilizing textures everywhere to store pre-computed lighting values, to store reflections, to store refractions, and so on, to be used by the Fragment Shader at a later point. But the idea is that is very similar. So each of the object vertices in your scene actually have a corresponding texture coordinate, i.e. a UV. And those UVs are going to map to positions in the actual texture maps, which are stored in memory on your GPU, your graphic card. And you can apply them however you like. So the UVs can be something where it's almost like you've unwrapped the object into like a sewing pattern onto the image, or you can do things like cylindrical mapping, spherical mapping, planar mapping, and so on. There's various different ways that you can map the texture to the actual object. And then the idea is that now that you know which vertex corresponds to which point in the texture, when we go into the fragment shader, we can compute the UV position between, so we know where we are between the vertices, and then we can figure out, okay, well then I need this. We interpolate and we get the specific position of the texture that we need to color that particular pixel. And we store everything in textures when it comes to the rendering pipeline. That is your primary mechanism for storing information is the texture buffers. Now, OpenGL and DirectX, they provide many different ways for which you can apply textures. You can have the texture be repeated. So instead of having one big texture just wrap around, maybe you want to repeat it. And you've seen this before in many games, I'm sure. If you look very closely at like the grass or like a hillside or a mountain, you can probably actually pick out the repeating texture block. And as beautiful as a game as Breath of the Wild is, this is one of my little pet peeves about it, is the fact that you can actually see the texture repetitions. And I get it's a huge game, so doing anything else probably would have been infeasible, but I still think they probably could have done something about it. I'm not saying used a larger texture, but just had, a pool of different grass textures that could work together so that you're not repeating the same block over and over again. You can actually see it. But that's what it would look like. GL repeat, which is just you repeat the texture over and over so that you wrap it around. Other things that you can do is mirror and repeat, which kind of gives you this book-ended appearance. You can clamp to edge, which just takes whatever pixels on the edge of the texture and stretches it out so it looks really goofy and silly. Or you can do clamp to border, which just says only the texture part, and I would not do anything else. And that's kind of what you want for labels, right? For like labels on bottles. So there's different techniques that you can use to actually project the texture onto the UVs or the vertices of the image, but there's also different ways that you can handle the texture itself in terms of repetition or just stretching it out. Sorry, I keep hitting my mic with things. Repetition is probably the most common. So, is this all photorealistic? So, not really. We don't really have photorealism because none of these things, how we're doing shadows, how we would do reflections and refractions, and these ideas of using textures, well, the way we're doing the shadows and stuff is not a perfectly photoreal way of doing it. Certainly, with really high quality mesh, it could look very realistic. And the same is true for doing things like the reflections and the refractions. You have really high quality meshes, like really small triangles, like sub-pixel size triangles, micro polygons, then it can actually look very realistic. But the rendering pipeline is getting its realism not from its techniques, but from the quality of the materials that you are using. So it's using high quality meshes, high quality textures with realistic appearances to them. That's where our photorealism in this pipeline is actually arising from. Because what we tend to get from the pipeline as it stands so far is a lot of artifacting, a lot of aliasing. It doesn't look so great. Let me demonstrate. So this is something that I rendered, 18 years ago? Some number of years ago, anyways. This was done using OpenGL, so this was done using the rendering pipeline. And it's comprised entirely of cones, truncated cones, and spheres. That's it. That's all that this is made out of. And this is actually like a posable puppet. You can pick up any of these joints in the neck, in the wings, in the legs, in the feet, and you can move it around. It's not that it matters. But this a low quality model and a low quality texture result in a low quality result. And you know what? This is also true of ray tracing. Yes, the lighting computations are going to be more realistic in ray tracing, but if you have a bad model and a bad texture, it's not going to look good. So that's what you end up with. We could up the quality of said textures and models. So this is actually a screenshot from the Ocarina of Time, which was released sometime in the 1990s. I actually just subscribed to the Switch Online update so that my daughter could get this game to play. Because I think she's played through Breath of the Wild now like 3 times. So, you know, got to start her on a new Zelda game. So here we have, you know, the quality of the models is certainly better than what I did. I'm not a modeler. And the textures are better than this. I didn't have any textures. This was just basic lighting. It's not photoreal though, because again, the quality of the meshes and the quality of the textures is not that great. And you can see here the shadows are really poorly done. They're not even using shadow volumes. They're just rendering a dark circle where the shadow is. It sort of works. It was really great for the time, of course. Super popular game. What about this? Is this a photo? Or not? Looks really real. I have been to Monument Valley and Grand Canyon in the United States, and this does look awful real. It's not. This is rendered. This uses the rendering pipeline. This is not doing ray tracing. This is Unreal Engine 5, and this is beautiful. Very, very beautiful. And that being said, I think they could have taken this image a lot further. I don't find the lighting in this image to be particularly interesting. It's just missing something. But it's still so detailed. And most people would be tricked into believing this is a photo. It's not. Here's another shot from Unreal Engine 5. Again, this wasn't ray traced. And yet one more of these statues, and what looks like Petra, except it's not Petra. Again, this is Unreal Engine 5. Now this one here, even though it does look photoreal, again, there's something off with the lighting, I find. Maybe I'm just being super fussy. But look at this. This is photoreal in many, many ways. So how are they doing this? Because what we've got back here is very, very far from this. So what separates these images? For number one, they're pretty much, all of these images were rendered using the same pipeline. Obviously, some of these are older versions of the pipeline than the Unreal Engine 5 ones, but some of the other differences were higher quality meshes. The ones from Unreal are significantly higher quality. The textures are much better for the ones for Unreal. But they also have more realistic lighting models because they had shaders. They didn't have shaders for Ocarina, and I was not using any fancy vertex or fragment shaders for that funny creature. They also have the ability to do atmospheric effects, and if they wanted to do some ray tracing computations in those individual shaders, they could do so. But at the end of the day, they're all still using that same rasterization pipeline. One of the things that we can do, and I've mentioned it a couple times, to improve the quality of our rendering is this thing called micropolygon rendering. And the idea is you're going to take a model as you have it, and you are going to further tessellate it, that's divided into more and more triangles, until the size of the triangles or the quadrilaterals are smaller than a pixel. And you do this so that when you're doing any of these triangle rendering, you're doing it at a very precise level. Because before, the triangles were big and like covering the whole background, you know, things like that. There are algorithms to perform this tessellation, to take like a basic model and to turn it into a micropolygon model. Ray's algorithm is one of them. We're not going to get into it. One of the downsides, of course, of micropolygon rendering is the number one, you are performing this tessellation operation, which could be computationally intensive because you're taking something from being like 10,000 triangles to like a billion triangles. Yeah, it's going to cost. But also, now that you have 10,000 triangles, think about the rasterization step, where you have to go through the list of triangles and actually rasterize in each and every one of them. Well, now you've got more, so it's going to take more time. This is me balancing costs to quality. So just to give you an example of the difference between ray tracing and micropolygon rendering in the Mantra renderer for Houdini, I have some example images. So here we have the sphere. Why does it look all blocky? Because I'm not rendering the sphere with a lot of triangles. And here's micropolygon rendering. You'll notice it's still blocky, and that's because I didn't tell it to actually like subdivide the sphere. You might notice that there's no difference between these two images because there's not really a difference between the two images. Micropolygon rendering in the Mantra renderer does actually a lot of ray tracing computation, so you almost always end up with very similar results. So here's another one where I've used the car paint shader because I like it. This is ray traced, and this one here, yes, I did change slides, is the, you can see the number at the top here is proof. The second one on 47 is the micropolygon rendering. It's pretty good, right? Now, as I said, one of the problems, of course, of micropolygon rendering is you're taking a mesh of 10,000 triangles and turning it into a billion triangles. And that's going to be computationally intensive. But there are little tricks that we can use to reduce those costs. One of them is this concept of adaptive tessellation. And the idea is not everything needs to be turned into a billion little triangles. If you have a flat wall plane, I don't need a billion triangles to render the flat wall plane. It's a flat wall plane. I can probably render it with one quad. So adaptive tessellation is going to take into consideration the type of object that you have and then make decisions based on the object type as to whether it needs to be tessellated. Ooh, excuse me. So, for example, curved surfaces or anything that actually has, a shape. So, some baby clippers here. And there's lots of different details to this. So I might want to tessellate this into smaller pieces, but I wouldn't want to put as much detail into this as I might want to put into something else that has even finer details. The nice thing about this idea of adaptive tessellation is the fact that now I have some objects which have big triangles or quads and some that don't. And the ones that have the little ones are the ones that need more detail, which means in general, I've reduced the total number of triangles in the scene. And you always want to reduce the number of triangles in the scene. Micropolygon rendering actually opens us up to a lot of really cool things that we can do, like displacement mapping. That's not to say you can't do displacement mapping without micropolygon rendering, but micropolygon rendering makes it easier. The idea is you have a flat surface, like this book. It has a nice, shiny, flat surface, and I want to make it a brick wall. Now, traditionally, we would use bump mapping, where we apply this bump mapped texture, like these ABC here, and it's going to alter the normal of the surface such that when we perform the lighting computation, it looks like it's in shadow or closer to the light. It's not, it's fake. And you can always tell because if you looked at the object's edge, if the lighting on the object doesn't match the flat edges on the side, then you know that it was just a bump map. But what displacement mapping does is it says that's not good enough. I actually want you to manipulate the mesh itself and actually create those bumps. So displacement mapping, instead of altering the normal of the surface, although it definitely does alter the normal of the surface, what displacement mapping does is it actually moves the vertices themselves, and the normals change as a result of the actual mesh changing shape. So if you look at this, here you have an original micropolygon mesh with really small triangles. We apply this displacement map, and what it's going to do is actually physically alter the mesh by moving the vertices. How do you move the vertices? I could move it this way, I could move it that way. But traditionally, when you do displacement mapping, the vertices are being moved along the surface normal at that point, or the vertex normal. So if you've got this and you do a displacement map, you're going to be moving the vertex up its normal, some distance corresponding to what the displacement map says. Now, how does that look? Well, here I applied the brick bump map to a sphere, and it rendered kind of funny in Houdini, and I'm not sure why. The point I want you to look at, though, is that it's not that interesting. This is a brick texture. You can obviously see that there's some funky business going around with the normals, but when I look at the edges of the ball, I can see that they're perfectly straight for each of the segments. In other words, we didn't actually change the shape of the ball. So this is bump mapping, and this is displacement mapping. Now this one you might be like, well, it's definitely more obvious that the brick texture is here, and it definitely looks like it's an actual, bumpy object. But when you look at the edges of the ball here, you might be like, well, they look pretty flat. And that is because for this particular image, we haven't actually performed a large displacement of the vertices. In fact, it's a very tiny one, which isn't necessarily visible along the edges, but it is visible when we're doing the lighting computations. And in many of these tools, you can actually modify the amount of displacement that happens, causing it to move further and further down the vertex normal. So this is the exact same displacement map applied to the exact same ball, but now I have increased the amount of displacement. And now you can actually physically see from the edges of the ball, this is a brick wall. It's cool. This is what we wanted. And we can go really crazy and do crazy things like this. And I can turn this ball into a sea urchin if I want it. You want to see it? You want to see the sea urchin? Let's do it. Let's open Houdini. Let's go over here. Oh, that's the wrong one. Never mind. File. Let's open a scene. No. Let's just do a new scene. New. Let's go to new. We'll come back to that scene in a minute. Here's our ball. And then we're going to go into our material palette, and I'm going to just take a basic diffuse material, and then up here I am going to go to OpenGL, and there's surface, and then displace. Actually, that's not the one I want to do. Let's not use that material. I don't like that material. The material doesn't have all the things I want to do. So in general, if you're using Houdini, the shader that you want for materials, if you're trying to make something you want it to look a certain way, but you don't want to do a lot of customized work, you want to use the principled shader. So we go there, we go to displacement. This is the one I want. And then when it says enable texture displacement, click that. And then you're going to go down here to texture path. And I like to choose, this was bricks, so bricks height, accept. And then we go into render view, and then let's render it really quick. This should only take a couple seconds. We don't really see much here, but we can change that. What we can do is we can scale it. And for some reason, it's not working for me today. I'm not sure why. Oh, I forgot to apply the material. To apply the material, click on the material from this tray over here and drag it onto the actual object. And there you go. We made a sea urchin. Oops. And this was done by doing the brick displacement texture. But what you can see here is I can actually adjust the offsets. So I can make it like 10. And it goes crazy. I think 0.5 was the default, and then we can like do the effect scale. And you can see here, as we adjust the effect scale, we are changing how much we are scaling the displacement by, which is pretty cool. Yeah, that's fun stuff. Displacement mapping, and it only took a few seconds. So that's fun, we can have a displacement mapping. So we've got our rendering pipeline. We know roughly how each of those components, we can do shadows, we can do reflections, we know how to do them ray traced, we can see roughly how they would work in the rasterization system. We know that to use micro polygon rendering or really, really, really high quality meshes, that's lots and lots and lots and lots of triangles, in order to get more realistic results. Now, we want to talk about the shaders themselves. What are they? So to refresh your mind, from the beginning of the lecture, I said that these were little tiny programs that are executed at various parts of the pipeline on the GPU to do some kind of task. For example, in order to do micropolygon rendering, we need to perform a tessellation, which is break things up into even smaller and smaller pieces. And we can do that in a shader. It's a little program that runs on the GPU that does a job for us at a specific state in the rendering pipeline. We can use these shaders to do the displacement mapping. In fact, you can do that displacement mapping in a vertex shader or a geometry shader, where we're actually going to be manipulating the positions of the vertices. You can do bump mapping. You can do texture mapping in a shader. Any kind of ray tracing component, let's say you actually want to do ray traced shadows for your rendering pipeline, you can do them in a shader. You can do computations of the light. You can do global illumination. You can do fun things like toon shading, and we'll talk more about that one later, just not today. Lots of different things that you can do to alter the geometry and the appearance of an object using a shader. Just to remind you where those shaders come into play, this was our rendering pipeline picture, and you can put a program in any of the green components. And the different kinds of shader types that we have, the primary types, the ones that we really care about, are the vertex shader and the fragment or pixel shader. And then some people will also talk about the geometry shader. Now there's one more that's not listed here. One of the things we've realized is that graphics cards are really good at doing the same operation over and over at the same time. Your CPU, however, your computer's processing unit, actually can't. It can do some at a time, but it can't do as many as a GPU. A GPU has thousands of computation cores. And as a result, they can perform the same operation 1,000 times the same time. And we have learned how to actually push regular programs onto the graphics card in order to take advantage of the shaders. Because the shaders are little bits of code that run on the GPU. So we are now writing like scientific applications, machine learning applications that are actually written like a shader so they can run on your graphics card. And in fact, the very first general purpose graphics card programs were just manipulating shaders. You're using the rendering pipeline to do machine learning, and it has nothing to do with graphics whatsoever. You just want the code to run on your graphics card. So that's a really fun thing. And there's lots of different languages you can do to actually do that. So what kind of languages do they actually use? So probably the most common one these days is GLSL. That's OpenGL's shader language. I think at one point it was called HLSL, and I'm not sure why. There was another one called SH, which was from RapidMind, which was actually one of the first general purpose GPU shader languages, and I'm not sure what that one is called anymore because RapidMind got bought by Intel, and I don't remember what happened after that. There's other shader languages like Vex, which is used by Houdini, although Houdini can also use GLSL. There's CG, which is from NVIDIA, although I believe that one is deprecated now as well. There are many shader languages, many. They are, in my experience, they are a C-like language with some interesting limitations and some different types. So if you're not someone who's comfortable with that, a lot, and many artists are not comfortable cracking out some C to figure out how to render something. A lot of the different applications for rendering have actually provided you the ability to create shaders like a graph. And we'll show you some in a minute, and we'll talk about how they correspond to the code as well. But these, regardless of how you create the shader, it gets executed on your graphics card, which means it's going to go real fast. And typically, and I say typically because we don't technically have to do this, these shaders would be altering the appearance of an object, so displacement, color, and so on. But technically, we can use these shaders to do whatever we want on the GPU. Personally, if I'm going to do general purpose GPU programming, I prefer to use CUDA, which is NVIDIA's own platform for doing that particular task. Now, you might be wondering, I'm sitting here and I'm talking up graphics cards like they're this amazing computation thing, and they're so much faster than your CPU. And you might be sitting there wondering, well, why don't I use the why do we have a CPU then? Why don't we just do everything on GPUs? Graphics cards are very good at very specific tasks, but they are not very good at general tasks. And in fact, they're not good at if statements. Any kind of conditional branching, they're really bad at. Whereas your CPU is very good at that, actually, and it's very good at general purpose computations. So while there are certainly many tasks that can run faster on a GPU, there are other tasks that don't benefit from it. Yeah, we have CPUs because they are a bit more of a general purpose computation device, whereas a graphics card is a very specific kind. All right, now I want to dive into some of the different kinds of shaders. So there's vertex shaders. And this is typically at the beginning of the rendering pipeline. And these are shader operations that are applied per vertex. They are one-to-one, which means they input one vertex and they output one vertex. They can output other things as well as a vertex, but it's one vertex in, one vertex out. You cannot use a vertex shader, at least in the languages I've used, to manipulate groups of vertices. That's a different kind of shader. So we could use a vertex shader to move the vertex along its normal. We could use a vertex shader to alter the vertex normal for bump mapping. You could do any vertex-based lighting computations. You could apply UVs that were computed by some other technique, such as spherical projections. We could do a spherical projection to compute the UV for that particular vertex. Lots of different things. We often also use vertex shaders to prepare or pre-compute values that will be used by the fragment shader to figure out the final color of a given fragment. And the values would be stored, they can be stored in a data structure, or they can be stored in a texture. There's lots of different ways we can do that. So what does the shader language actually look like? So this is an example of GLSL, which I've taken from the Learn OpenGL shader section, because I do have shaders written in GLSL, but I'm not allowed to show them. They're under NDA. So as you can see, it looks very much like C, but there's some slight differences in terms of there's some different types. So something like a vec4 would be a vector of 4 things. So this is a vertex color, RGBA, A for alpha. And so this is the actual little vertex shader, and all it's doing is assigning the vertices all the color dark red. That's all it did. Very simple. So we take this vertex and we output a vertex color. That's it. But I just assigned all the vertices the color dark red. It's kind of boring, actually. Now, if you wanted to actually write some GLSL shaders, you absolutely can. I cannot speak for Maya. I have not used Maya in a number of years. But I'm pretty sure you can do this in Maya as well. And Blender. I don't know about Pavre, but you can definitely do it in Houdini. And what we've done here is we've actually created a new asset, a GLSL asset, and we have our vertex shader, a fragment shader, and a geometry shader. And this is actually where you can actually type GLSL language, and you can compile it into machine language here and test it out to actually customize, you know, if you want to make your own vertex shader, here you go, do it. And it's got all of the components that you need in order to integrate that with Houdini right here. So all of the different variables that you might have access to. And here I actually wrote a shader. This shader here, what did I do with this shader? Oh, I was assigning, I think, just looking at it. I was actually perturbing the vertices, so I was moving them randomly a little bit so they wouldn't be so boring. Kind of like writing a displacement shader, except I just did it randomly. Yeah, then you can compile it, and there you go. There are other ways of doing this. So this is another way of perturbing the vertices, so actually moving them around randomly. Except instead of using GLSL, I used these node networks in Houdini. So I have, I'm going to zoom in here. So what I've got is I've got this geometry, and P is the positions of the vertex. So for each vertex position, I have this turbo noise function I'm going to call, and it's going to take the position and apply some noise to it, and then I am going to displace that vertex afterwards by the amount that's determined by this noise function. And then I set the vertex position to be the result of displacing the input vertex by some amount. And this is kind of the same as what I did here, except I didn't use turbo noise here. I just did rand. But it's the same idea. These node networks that we're using to create this shader to manipulate the vertices, I could either do it with this graph approach or node network approach, or I could write GLSL code. So that's kind of cool. Now what's interesting, as we're going to see, is that the GLSL program actually corresponds to these blocks here. You could take this node network and literally just write it out as a piece of code, because how these things connect together and what they each represent is function calls, inputs and outputs. It's just another way of visualizing the program. And I applied the shader to it, just a material to it, just so you could see. But this is what it did. It created this nifty little sphere. So this actually did start out as a sphere, by the way, just a basic sphere. And I applied some turbo noise and used the turbo noise to manipulate the position of the vertices. Well done. Pretty cool, right? Shader without any code. And you can actually do that, by the way, in Unity and Unreal, and I'm sure you can do it in Maya as well. Again, I haven't used Maya in a long time. You can usually create the shaders just using that kind of network design. So you can also do a geometry shader, which runs after the vertex shaders have run. It's completely optional. You don't have to do anything with it. But the idea behind a geometry shader is, instead of getting just one vertex in and one vertex out, you have the option of getting one or more vertices that belong to a primitive in, and you can output any number of vertices you want. So the idea behind a geometry shader is you could take like a sphere that's made of, 10,000 vertices, and you can downsize it to like 100 vertices. Or you can upscale it to 1,000,000 vertices. So geometry shaders actually let you manipulate the geometry more than just pushing things around. It's actually going to allow you to add and remove vertices from the primitive itself. And geometry shaders, because they operate on the primitive as a whole, you can actually access and do things to other vertices as well, which is kind of cool. In particular, we tend to see geometry shaders for tessellation. And in fact, if you go back to this pipeline diagram, you'll see that the geometry shader kind of happens after the tessellation phase. That's not to say you can't do further tessellations inside the geometry shader. The other things that you can do is maybe you want to do quads instead of triangles, or triangles instead of quads. You can do all kinds of things like that. Then the last really important shader we run is the fragment shader. And this is also known as the pixel shader. This is what we use to gather everything together to give us the final color of our pixel. Now, what is a fragment? So a fragment is just a really small section of an object that's visible, and it's often pixel sized or sub-pixel level, and it is entirely possible that your pixel could be comprised of several fragments. Like a vertex shader, a fragment shader is one-to-one. You get one fragment in and one fragment out. You do not get multiple fragments out. You don't get to manipulate the size of the fragment. And what we're going to do in the fragment shader is perform the final lighting contributions. This could be done by sending rays, or more often than not, it's taking the per vertex lighting computations that were already done and interpolating them to get the color of this particular fragment. It's taking the texture points, finding this particular position, and getting that pixel from a texture lookup. So for example, and this example is from the Learn OpenGL page, you could have a vertex shader that assigns each of the vertices of the triangle a different color, and then the fragment shader is going to run and it's going to perform some interpolation between the three vertices and then use that to compute its final color, which is pretty cool. Now I went into Houdini and I created my own material shader, and a material shader is a kind of fragment shader where some of this might be happening in the vertex shader or information that's available, but this is where I'm gathering up all of the final pieces to get the final color. And you can see here we have a much more sophisticated node network for this. We've zoomed in. So I'm using the classic shader core, which is just your basics. I'm getting an input surface color from the object, and then I am applying various noise and random numbers to it and adding those values up and setting that to be the diffuse color. And I can also do things like set the opacity. In here I set a random opacity. I can set random textures. There's all kinds of cool stuff you can do. And each of these little subnodes is it's just like a little box you bring up, and this, like, you could turn this into a GLSL program if you knew what each of these little boxes corresponded to in terms of function. And there's the material that I got. And then if I want to do a little bit more, because this little blowy, blobby thingy, I don't know what it is, but I figured let's make it like a piece of weird bumpy glass, or creepy cloud. So there you go. I modified some of the different components of that shader program to give me my own custom look. And if you want to create pearl effects, if you want to create a really good skin effect or a very specific material, you're going to want to create your own fragment shader, your own material shader to represent whatever surface it is you're trying to create. All right, now I already talked about that. So some of the last topics we want to talk about today are simulating ray tracing with shaders. So you can, as I've mentioned throughout today's lecture, actually simulate ray tracing using these shaders, because what you can do is inside the vertex shader, inside the geometry shader, and the fragment shader, you can actually send rays. you can actually perform the ray tracing computations in the individual shaders themselves. Now, doing that obviously is going to take a big hit in performance because you would only be getting rasterization for the rendering onto the screen, but the actual lighting computations would be done using the ray tracing methods. True story, that's actually what Houdini's doing for micropolygon rendering, which is one of the reasons why it's so slow. The advantage, of course, of this is, you know, or at least of the rendering pipeline, is it's customizable. I get full control over how everything is rendered and what the final look is. So, as I said, we see these abilities in many, many different tools, and you're welcome to check them out in things other than Houdini, but it's fairly straightforward to do in Houdini as well. So just kind of an overview discussing performance. So ray tracing and global illumination, as we know, is very, very expensive due to the number of ray object intersection tests we might have to perform, how many rays we're sending, and so on and so forth. But this nice thing about ray tracing is that so long as you've set yourself up a really nice image, you get a really nice result. That's very convincing. Rasterization, on the other hand, is very much a faster technique. There are no ray object tests, which means that it's going to be much, much, much faster. And it can simulate the light interactions. We can use programmable shaders and textures and so on to create the appearance. But from a general perspective, rasterization is not as accurate in terms of lighting. And you'll see that in games, you'll see that in movies and so on, where they've used lower quality versions of the reflection maps and so on. Ray tracing just does a better job of those things. So I want to show you just really quickly how to do a couple of these things in Houdini. So I'm going to open it up, and I'm going to delete that. Oopsies. So I'm going to go and I am going to open my shader file. And you can see here I've got this lovely object. I did not use a displacement map. This is me actually using noise instead. So I am going to go into, so I go to this object tab here in Houdini. And this started out as a sphere object, which is right here. So I'm going to go into the sphere object. And you can see here I have this network. And in order to manipulate the vertices, I created this attribute VOP. And if you right-click in here, you have all of these different nodes that you can add to the network. And there's a lot of them. And so the one that I manipulated is this attribute VOP. And inside here, I wanted to manipulate the vertices. So I have the input geometry position here. And again, this is the vertex. And then I call turbo noise to create a random number based on a noise function. And then I use the amount of noise to displace the vertex by some amount equal to what was specified by the turbo noise function. And then I map that back to the geometry, and that's how you get this lovely bumpy object that's actually just a sphere. So I can actually show you this. So there's with it off, and there's with it on. So, oopsies. I disconnected it from the sphere. That's what happens. See, this is the input to this function here. So that's the sphere, and when we apply this shader to it, we end up with this bumpy red box, which is pretty cool. And then the materials. So I created this diffuse material here. So if I double click on this diffuse material, you can actually see here that we have been playing around with the material. Looks like I clicked on the wrong one. Diffuse one, there it is. Or maybe I don't have any more. But the idea is I can actually create different things here. So that's kind of fun. All we have to do is to go into our palette and click on our object, and there we have our network, and we can go inside. So I had this diffuse network here, and this is the one that I just created earlier for this. So what I did, you can see here, so I created another periodic noise. So I take the position of the object. Actually, no, it looks like I took the UV coordinates for the object's vortex, and then I created a noise value from it, and then I did a second random noise one from the color, and then I add my noise to my color, creating this add node. And again, to create things like add or multiply nodes, you right click, and those things are under math, so we could go to math add or math multiply to manipulate those things, and then we can take the output of that function and pipe it in as the input of the next one. Now what's really interesting is you see where we've got add, random, noise, and all these lines connecting these things. This is just a visual representation of the GLSL code underneath. There's nothing to be afraid of. And you can do all kinds of crazy custom stuff. And it's all available from this lovely right-click menu. So just to give you an example, what if instead of adding the noise to the color, what if we multiplied the noise by the color? So to do that, I would do math, and then I'm going to choose multiply. And then I'm going to take the noise, and I'm going to take this random here. And then I am going to take the product, and I'm going to set that to be the diffuse color. Okay? And then I'll go over to the render tab and render it. And there you go. So now instead of adding noise to the color, I multiplied the noise by the color, and then we get that cool picture there. So just to give you an idea of the difference, this is with adding, and then if I switch that to multiplying, you get a shinier object. This is pretty neat, right? So I just created a shader for this completely without any programming whatsoever. And these are fairly easy to create, and in the tutorial notes that we will have posted, there will be some videos to show you how to do some other really cool shaders inside of Houdini. All right, so that is the end of our discussion on the rasterization and shader pipeline for today. In our next lecture, we are going to wrap up the topic of photorealistic rendering. We're going to talk about real-time ray tracing, real-time global illumination techniques. We are also going to take a look at some of the little odds and ends we hadn't considered so far, so things like stereo cameras and so on. And then lectures after that, we'll shift to the non-photorealistic side, where we no longer care how real it looks like. Now we just want to make it look cool. And we'll look at some different techniques to achieve that, shaders and all those kinds of things. So we will see you then after your reading break. So I hope you have a great reading break.